Hey everyone, hello. My name is Arnab and welcome to my YouTube channel. I'm a software engineer by profession and a problem solver by heart. So I came across this wonderful lead code problem, and in this video we'll be going through that and try to solve it out. So let's get started. Okay, so the problem name is minimum genetic mutation. What does it say? Gene string can be represented by an 8 character long string with choices from A, C, G, and T. Suppose we need to investigate a mutation from a gene string start gene to a gene string end gene, okay, where one mutation is defined as one single character changed in the gene string. Got it? So basically, if it's a gene string that is composed of either A, C, G, or T and total of 8 characters. So is this mutation from AACCGGTT to AACCGGTA. This is considered as one mutation. Okay. So there is also a gene bank that records all the valid gene mutations. A gene must be in bank to make it a valid gene string. Okay. Given the two gene strings, start and end gene, and the gene bank, return the minimum number of mutations needed to mutate from start gene to end gene. If there is no such a mutation, return -1. Note that the starting point is assumed to be valid, so it might not be included in the bank. All right, okay. So, so we have been given a gene string that is initial gene string, as you can see from the example. Gene string is this, then and the end gene is start gene is this, and end gene is this. And in the bank, if we have this, bank is effectively an array of gene strings which are valid possible gene string. Okay, and what we have to return is m- the minimum number of mutations. So return the minimum number of mutation needed to mutate from the start gene to end gene. So from if I have to go from AACCGGTT to AACCGGTA, and since my gene bank contains AACCGGTA already, that means this is okay. That validates one thing, that this is a valid gene st- intermediate state of the gene. So if I have to move from, can I move from gene start gene AACCGGTT to AACCGGTA? Yes, I can, because there is only one character one character. So this is a valid mutation. Okay, so there is only one mutation that we would require. Fine. And to move from the start gene this to end gene this is, and in the gene bank we have these all values. Uh, so can I directly move from here to the end gene? Okay, I can't, because there are two character changes. So if you see um, this one and this one, right? Because A is C and this is A, and here also at the end you have this T, but here you have A. Rest all the characters of the string remain same. So effectively we need to make some transitions, or in the problems in the problems words, we need to do some mutation from the start gene, go all the way till the end gene, and return the minimum number of mutations. So if I just take this as an example, let's try to understand this a bit more. Okay, so we need to go from this. That is, this is the gene string to um, and this is my last end gene string. So this is your start gene and this is your end gene, and we need to go from here to here and need to say how many need to return how many number of mutations are that are required. uh, the gene bank contains these all values. So okay, these are the gene bank values. Mm, okay, so I can, okay, the way to go about solving is solving this problem is, if we have the start gene here, then I I can move from the start gene to any of these intermediate gene string, and I can do multiple number of hops in these intermediate gene strings because these are the valid bank. And at the end, I should be stepping onto the end gene. Then I would be able to say that this is reachable. The end gene is reachable from the start gene, right? And in the process, I should also return the minimum. In the process, if I'm able to reach from start gene to end gene, I should return the minimum number of hops that I took. So if from the problem, it looks to me it can be solved using BFS, but the crux is we need to have a graph that is created out of this entire problem statement. So let's try to do that. So if I just represent it in term of a graph node, we can have like this. All right. So if these are my nodes, let's see. And how do we decide that I can go to any of the gene string is, um, if there is a character difference of one present in the two between the two genes that we are trying to make a hop. So what I mean is, if AACCGGTT is the start gene, and these are all the genes that are present in our gene bank, we can construct a graph something like this. Can I go from this one to this this gene? Yes, I can, because there is only one character difference. So let me just okay. Okay, first of all, this shouldn't, one good question to think about, one good concept to think about here is whether it would be a directed edge or an indirected edge. So it should be an undirected edge. Reason, because if I can move from here to here, it's always possible to move vice versa as well. So if I have to draw, I can just like this, and then what all nodes can I visit from here? AACCGGTT to AACCGGTA. Okay, and from this, can I move to from this? Can I move to AACCGGTT to AACCGGTT? Okay, no, I can't move to this. I can't move to this as well. And can I move to this? Oh, this can't. This also can't be visited. So can I move from AACCGGTA to AACCGCTA? Yes, I can, because there is only one node difference. Can I move from here AACCGCTA to GCTA. Okay, I can't move from this one to this one. Is because there is one character difference A here. CG CTA. Okay, I can't move. I can't move. Okay, from so I can't move from AACC to any other node, I guess, because I would need one change here and in the third character, and I would need okay, I would incur multiple character changes. So this is not possible. And can I move from here to here? That is also not possible. So let us look for this. I think there from here we can move to this because there is only A C C G G T A. So this is C A triple A. So this is A C C G G T A. Yes, we can move from here to here because if we just change this character at third position, we should be able to move. So similarly, then let's see what other um, so I can clearly see one path here, but let's construct this graph fully. Can I move from, if I can't move from here to here anywhere, to can I move from AACCGGTA to triple ACGGTA? Triple ACGGT. Yes, we can move from here to here. TA. And can I move from here to here? Triple ACGGTA. Okay, this is the last node itself. Okay. All right. This is the last node. Okay. So then I have to also think, make sense. We need to also create a set out of this. So let's jump. I think we have a rough idea on what to be done. So we need to represent this entire gene strings, including the start gene and end gene as um, as a nodes in your uh, graph, and then the solution is effectively doing a BFS call from your start gene to end gene, keeping the number of hops in mind. So the result, the number of hops that you get would be your solution. And if by any chance we are not able to reach from start gene to end gene in one iteration of not one iteration, but like after completing our BFS call, that means this end gene is not reachable. So okay, so let's get back to the let's jump on to the solution. Okay, so let's start with the solution of this. So we have been given a function called min mutation, start gene, end gene, and a bank. So for our first thing that we should do would be we need to have a graph, and let's represent this graph in a form of map of string. So it is an adjacency list, and we could have it as a vector, but then we also need to store a reverse index mapping from the string to the vector. So that's why it's good to use it as a map of string where the key would be your source gene string, and to a vector of strings which are basically all the gene strings where I can go to from this source string. So let's represent this like this, and yeah, we need to construct this graph now. So what we can do is uh, so let's say, and here the one thing we should notice is Note that the starting point is assumed to be valid, so it might not be included in the bank. Oh, so it might not be included in the bank. So that means this may not be there in the bank from the start date, and but the end would be there, right? So what that effectively means, it might not be included in the bank. It might not. Okay, that's a tricky thing. Um, so that I don't know whether it would or it won't surely to do this. Maybe what we can do is okay. Let's for now assume that your start is not there. Start gene is not part of that, and proceed ahead. Oh, actually, we can't. So better would be, let's create a set of string. This would be a temporary set, and in this set we are going to insert start gene, and okay, and as well as let's insert the end gene also. That's not assume anything. Okay, why I did this is because we need to have there is a possibility that the start gene would be part of this bank, and the engine can also be part of would most likely be part of the bank. We don't want these nodes to be repeated um, while constructing of our graph. So this is just to be in a safer side. So let's so we do have a set now, and if we have to construct the graph, we can just pick the elements and see if there is a common difference between the strings comes out to be one, then there is an edge that lies between them, right? Okay. For simplicity, let's say we have a temporary vector, and mm, okay, can I not traverse on that entire set? Let's see. Um, Set iterator traverse, different ways to iterate over. And so okay, we have this begin iterator and iterator, and how to find the next element of the set. Oh, okay. Data structure functions like C++ STL. Oh, it next, right? Okay. Um, let's do that. So for we don't need this. So that means um, let's construct a graph out of this. Mm, what we can do is iterator um, st dot begin. Okay, and iterator is not equal to st dot end and iterator plus plus. So we are traversing on that set, um, and for each of the current element would be your the source element. So mm, string would be okay. Let's see, the cur current gene would be equal to nothing but this. Oh, okay. Why do I need to then store it? Let's see. iterator 1, which is equals to iterator next. Iterator is not equal to st dot end iterator plus plus. Okay, and if I have if can do mutation, can I do a mutation with among these two strings, iterator and iterator 1, then I'm going to create a node saying iterator dot push back, so iterator 1 and vice versa. Okay, sorry. So this would be okay, but this would be in a reverse order, right? So we need to implement this can do mutation. uh, we can do that, and what this will effectively do is, okay, so here we are starting from the first element of that set, we are going all the way till the end, but we are also initiating the second pointer iterator 1, which is starting from the second element of the current element where I am at, and going till the end, and it is saying if there can I do a mutation from the current element to basically from the ith pointer to the jth pointer. Okay, and if I can do, then I can do a mute, so I can create a no edge from that node to that. So okay, let's quickly implement this method as well. String can do mutation, so this is considering okay, so this is a string, right? Okay, let's say this is um, s1 comma string s2, right? And can I do my mutation? Then I need to see key how many character differences are there. So int char def is equal to 0, but um, then s1 dot size, um, I can do a mutation if my character difference um, is equal to 1. Equal to 1, then only can I do a valid mutation. Okay, so this is going to construct my graph. So let's say construct graph. Okay, all right, now we are going to do BFS on this. So to do BFS, so as I had mentioned here in this, this will be a start node, this will be our end node. So we'll do BFS by maintaining a um, visited array, uh, which will tell whether that node is visited. So from here we can visit this one in one hop, then from here we can visit this one in one hop, then again we'll visit this in another one hop, and then we can visit this in one hop. Okay, so that means there would be one plus effectively one hop here, that is two. In two hops we will be able to reach from start gene to end gene. Let's try to code it. So if I have to do BFS, we need a queue, and queue would be storing the the current node, right? So that would be your string. So this should be storing pair of string, comma, what that current what is that node's current level, and let's call it this. Let's maintain a visited vector. Okay. For that we can use a set visited. Okay, and initially we can just add the current start gene, which is at level of 0, and um, let's mark this to be visited. Okay, and okay, now so we'll start off that BFS from that. So now until let's do the BFS now. So if until we don't see q dot empty, that means until I have element, you are gonna do a BFS traversal. So pick the first element. Okay, this would be the so current gene would be your q dot front dot first, and current mutation level would be q dot front dot second. Okay, now we have stored it, means we know the current one, and then we are going to check its neighbors. Okay, um, so we are gonna say, hey, what all nodes can I visit from this current gene, 2. Okay, and this would be less than this. Okay, this would be current gene, g of current job size I plus plus, and um, okay, so these are all the genes that I can visit from the current gene, right? I have to make sure if not of visited um, g of gene of I, that means that is not visited, then we need to visit it. So first of all, okay, this is wrong way. This visited dot find equal to this dot end. Okay, and if means you have sorry, if this is equal to end, means we have not found it in the visited array, so we need to do BFS traversal there. So let's add it to the queue, um, and this will be added as um, same the node. Let's copy this thing, and Okay. And the current level plus one, right? um, and mark that we start current neighbor as visited. All right, so this is going to visit all the neighbor. This is going to insert them into the queue. That means we are going to visit them next. And also we need to also we need to pop. Once we have done this, we need to pop element from the queue. Okay, one thing to also keep in mind is, okay, while I'm doing this BFS traversal, if I have found that um, node which is my end node, or which is the end gene, that means I have the solution. So if my end gene is equal to current gene, so I just need to return the level uh, that I the current level of that engine. Otherwise we might have already okay, so if there is no edge from this to this, we would start the our DFS our BFS traversal from here. We'll come to this in hop number one. We'll come to this in hop number two. Then we'll come to this again in hop number two. But we can't in any way visit this engine. So in that case, we'll be exhausting our BFS queue, BFS traversal, and then we have to return a -1 from here. That means there is no edge from there to from the start gene to end gene. All right, looks decent to me, but let's do a dry run because it's always good to do a dry run because if you are giving an interview, this would be a plus point for plus point. This would give a plus point to you uh, because we are not directly running it and doing a blind run, and that doesn't span out sometimes very well. Let's see if we have a mutation. We have a graph, we have a site. Okay, we are trying to insert all the bank, all the genes in the bank, start gene and end gene, and then we are trying to construct the graph where we have started from the first and till the last, and the second, the fast pointer iteration iterator one is moving from next till the end. Okay, do I need to have this next as a function? It's 2 plus plus of I, okay, but or let's try to initialize this as a function. Maybe this will work. Random mutation from this. Okay. Mm, today goes to begin. Okay. Next element of the set C++ STL. Okay, doesn't look like fine. Okay, if I do try, I don't know, let's keep it as it is. So iter one, iter, then you are going from next, and can I do mutation between these two? Then saying okay, and adding this, that push back, not push back, iter. Cool. So this should construct the graph if this is working fine, and then I have a queue visited. start gene, end gene. This currently and this is currently visited. So until popping the first element, that is your twice. You're going through all the elements of all the neighbors of that current gene, and if you have not found that, then adding that to the queue and marking that as visited and then popping it. Okay, looks correct to me. Let's do a run. Okay, what is this? What is it saying? Okay, I expected this. So no member named next in this. What does it mean? Can I do like this? Okay, no member name again. So this is pretty weird. So to solve this, can I auto next? Can I have iterator and here if I can use okay, current iterator current and let's see iterator current plus plus. Can we do this? So this is like a temporary variable that we have used. Okay, let's remove out the ampersand. Okay, what is it saying now? Visited is this expected. Okay, there is little formatting issue. Visitor dot find. Oh, there goes the problem out. I think this should. Oh no, again this would be a problem. Why? Why is there too many of this? Why? Hmm. All right, so something is wrong out here. Let's try to do some debugging. Let's try to first see if we have the graph correctly. Debug. Mm, and this can be used for debugging. Let's check this map for a sec. Okay, this is not key and okay, we have a key and these will be the values. Auto, or what will this value be? If you do an auto based iteration, then that will always be string, right? So what's the problem? Okay, let's search traverse or map C++ STL. I see. Okay, so this would be in a pair format. Okay. So this will be uh, key value dot first. So here you can just use keyword dot second and this. Then let's print this out first. Okay, that is fine, but where is it happening? Let's try to see. Set insert. Okay, 0 bank sizes insert. Oh, see, here is a tiny mistake that I was doing. Iterator 1, so this should be iterator. Okay, before let me show you the error. If I wouldn't have done this, still it was time limit exceeded, I guess, because there is some iterator. There is, we're not properly parsing, we're not properly traversing the iterators. Let's see if I put it like this: iterator 1 is, so all the compile time and runtime should go now. Iterator 1, iterator 2, and okay, for looks like we have got correct result, but also we do have the standard output. So from this, if this is a bank, what all nodes I am having? Triple A, C, G, T. So let's try to once double check with this. So for triple A, C, G, G, T, A, that is triple A, C, G, G, T, A, you have a you have an edge from AACCGGTA. AACCGGTA. Okay, yeah. Earlier it was there. I think I had removed it while explaining. So this is there. Then from AACCGCTA, CCGC, GCTA, AACCGCTA. Okay, you have a node here, and this one has the max. So this one is their second node, and the last one would be AACCGGTT. AACCGGTT has an edge from H to AACCGGTA. Okay, makes sense. So this is, yep, this is how we wanted the graph to look like. This is validated, as well as our answer that we are expecting is also correct. Let's try to submit it, but by putting this debug here, let's try to submit it. Okay, what is it saying? Start game for this is the start genus ACCGGTT, and what am I returning? This is a very edge case where your there is no edge a whatsoever from the start node to the start gene to end gene, and your bank is empty. That means, okay, there we might have created two nodes, but there shouldn't be any edge in this case. Why? Be any edge in this case? Shouldn't be any edge in this case. Mhm. Output that I'm printing is 1. I'm expecting -1. Yes, -1 should have been there because we couldn't complete. I think, let's see. Mm, what this, what are we getting if we have this, and what is the norm? At least what is the map that we are obtaining from this? Let's see. I think somewhere we have done something wrong. Starting. Oh, no, 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 not this case, please. Run on this, and bank does not contain anything. Oh, there is an edge from here, but but your bank does not contain anything. I see. Okay, so that means it is possible for the end gene to not be present as well, but this was not very much understood from the problem statement. Okay, in that case, you need to honor the bank itself. There is no other way to go. Mm, so I'm just wondering, in that case, do we even So in that case, mm, we can remove the end gene and let's, because if if we remove the end gene, then it is not guaranteed that you'll be always including it for the mutation. It will only be included if this is a part of the bank. And start gene, you're anyways on that start gene, so you can always move to any of the intermediate, so you can include that. So let's see. I think this okay. Yes, this had worked. So this was the small crux, but even though I didn't like very much this last edge case, because that was not too much descriptive from the problem statement. But this okay, but this can anyways happen, so it's fine. um, yeah, like it can be removed, cannot be part of the bank, so this is what the problem statement expects. So anyways, so yeah, I think we have the solution. Let's clean few things up here and do a submission again. Yep. So from this, okay, one wrong answer we got, but then we got two correct answer. So yep. Thank you, folks. Thank you for staying this along. If you have been, have a nice day, and signing off.